Consider a hollow hemisphere. Assume its mass is m, radius is r. The hemisphere's mass itself is m. Okay. I want you to derive its moment of inertia about a diametrical axis. So an axis somewhat like this. Yeah. So think carefully and try to solve this. Derive the moment of inertia of this hollow hemisphere about this axis. Any ideas, anyone? One of you tell me, what do we know about moment of inertia of a hollow sphere? This is a hemisphere, okay. We have never discussed hemisphere when it came to moment of inertia. But for a full sphere, full hollow sphere, what do we know?
Moment of inertia equal to 2 by 3 mr square.
About which axis?
About the center of mass.
Passing through the center. Okay. So if there was a full sphere like this, okay, I don't think I can close it this way. Never mind. If there was a full sphere like this, okay, then about an axis passing through the center, okay, vertically, horizontally inclined, any axis passing through center, it's called a diametrical axis. About that axis, it is 2 by 3 mr square. Okay. For full sphere, if it is 2 by 3 mr square, then for half the sphere, exactly half of it, how much should it be?
Square by 3. Sir.
Huh? What did you say?
Mr square by 3.
By 3. Okay, okay. 1 by 3 mr square. Do you all agree with this or not? Full sphere and half sphere. Half sphere is exactly half of the full sphere. Okay. And in whichever manner the mass of this half sphere is distributed around this axis, in the same manner, the other half's mass also is distributed. So they should be contributing the same amount of moment of inertia. Let's say this half's moment of inertia is I1, then the other half, if it existed, its moment of inertia also would have been I1 about this axis. And both halves combined is 2 by 3 mr square. Okay, then each half separately will be 1 by 3 mr square. Okay, that upper half is not even there. The lower half will be 1 by 3 mr square. Okay, you are given half of a system, then moment of inertia also will be half. That's the idea. Okay. Still, tell me the answer to this problem that is given to you. It's a hollow sphere of mass m radius r. What is its moment of inertia about the axis that I have shown?
Mr square by 3. Sir.
So 1 by 3 mr square, you are saying? No. This is one thing which you need to be very careful about while solving problems based on moment of inertia. I'm telling all of you. Imagine it as a full sphere. Okay, assume the full sphere was present. See, why the answer is not mr square by 3 is because this half sphere and this half are not the same. They are not same in terms of mass. Okay, the formula 2 by 3 mr square is for a sphere of mass m, not hemisphere of mass m. For a full sphere, if mass is m, then the moment of inertia is 2 by 3 mr square. Then for half sphere, it will become 1 by 3 mr square. What is this half sphere's mass? M by 2 only. Okay, what I'm trying to say is, for a full sphere of mass m, full sphere mass m, moment of inertia is 2 by 3 mr square. Then in that case, half sphere moment of inertia is 1 by 3 mr square. And in that case, half sphere mass is m by 2 only. For m by 2, you'll have 1 by 3 mr square. Then for m, what will you have? It will again be 2 by 3 mr square. Okay, you don't even have to imagine the full sphere. The answer is 2 by 3 mr square. Yeah, think this over once again. Ask if you have any doubts. Aishwarya, did you understand?
Yes, sir.
Okay. Rishi, is this clear? Yusuf?
Yes, sir.
Okay, fine. So you have to stay in touch with all the formulas, then only you'll be comfortable. Because suppose you don't even remember that 2 by 3 mr square, then everything will be confusing to you. Okay, so go through the formulas that we have derived. Anyway, had the full sphere had a mass m, then its moment of inertia would have been 2 by 3 mr square. And in that case, half sphere mass would have been m by 2, and its moment of inertia would have been 1 by 3 mr square. But in the given problem, half sphere's mass itself is m, not m by 2. Therefore, the answer will be 2 mr square by 3. Okay, let's solve some other similar questions. A semicircular disk. Semicircular disk is effectively a half disk. Okay, just a moment, I'll give you the diagram. Or, okay. Fine, I won't give you the diagram. You only think about this. What is it? Okay, it's a semicircular disk of mass m, radius r. Calculate its moment of inertia or express its moment of inertia about the base. Think carefully. Okay. Let's visualize the system first. Vanilla, your answer is correct only. Okay. The given system is a semicircular disk. But the semicircle's mass itself is m, not the total mass. Fine. Rishi, tell me, what do you know about moment of inertia of a disk? No response. Aishwarya, you tell. What have we discussed about the moment of inertia of a disk?
Sir, mr square by 2, sir.
About which axis? See, whenever you mention a value of moment of inertia, you have to mention the axis also.
About its own axis.
About its own axis. Own axis will be perpendicular to the disk. Okay. What else? Yesterday we derived one more result also related to a disk. Okay, about its diameter. How much is the moment of inertia?
Sir, mr square by 4.
By 4, correct. Okay. So listen, had it been a full disk of mass m, radius r, okay, if it's a full disk of mass m and radius r, then its moment of inertia about the diameter would be mr square by 2. Okay. If full disk moment of inertia is mr square by 2, Rishi, only tell me, what will half disk moment of inertia be? Which is distributed in the same manner. This half and that half are distributed in the same manner. So what will this half's moment of inertia be? It should not take that long. It is just half of it. mr square by 4. It would be mr square by 4. For the full disk, if it is mr square by 2, equal distribution, same distribution on both sides. You remove one side, then the other side will contribute mr square by 4. Half of mr square by 2. Okay. All this is true when the full disk has a mass m. Suppose the full disk has a mass 2m. Then full disk moment of inertia will be 2m r square by 2. And then half disk moment of inertia will be 2m r square by 4. That is mr square by 2. Okay, so for half disk about this axis, it is mr square by 2. Okay. Next, suppose there is a regularly shaped system. A disk itself you take. Full disk mass is m, radius is r. Okay, we know its moment of inertia about its own axis. We know its moment of inertia about its diameter also. Okay, own axis is mr square by 2, diameter is mr square by 4. Fine. Suppose from this full disk, whose mass is m, radius is r, some part is scooped out or removed. How are we removing? Like this. The part that we are removing is in the shape of a disk again. And you can see that the boundaries of the two disks are touching each other. Just a moment, I'll adjust this. So imagine this has been done. We removed this mass. Okay, full disk mass was m, radius was r. From that, some mass has been removed now. I want you to find out the moment of inertia of the remaining mass about the z-axis. Think carefully and solve this, all of you. Okay, okay, let's solve this. I got one answer as 15 mr square by 32. We'll see. The answer you have given is less than mr square by 2 only. May be correct. Rishi, can you repeat the idea that we are going to use to solve this problem?
Sir, we find out the moment of inertia of the smaller disk and then minus it with the whole one.
Yes, yes. So the idea is to subtract the moment of inertia of the missing part from the full disk's moment of inertia. Yes. Full disk moment of inertia is mr square by 2 about the z-axis. We know that. Let's keep it aside. Consider the small disk. Just a moment. Let me take the image of a disk. So small disk is approximately this much, around this much. Okay. What is the radius of that small disk? Anyone?
R by 2.
R
R
by
by
2,
2.
sir.
R by 2, correct. And see where the axis is. You can't change the axis. You want moment of inertia of the remaining system about the z-axis. So what you have to do is moment of inertia of the full system about z-axis minus moment of inertia of the missing system or missing part about the z-axis itself, about the same axis, okay, is what you need to do. So for this small disk, we have to express moment of inertia about this axis. Okay. Now we didn't derive a formula for moment of inertia of a disk about this axis. In fact, if you take the tilted view, okay, let's just visualize the axis properly. It's very important to know which axis we are deriving the moment of inertia about. So for the small disk, it is this axis. Okay. We don't have a formula for moment of inertia of a disk about this axis. Okay. Vanilla, don't answer. Anyone else? How can we find out the moment of inertia of a disk about an axis like this? You think of the ideas that we discussed about moment of inertia.
Parallel access theorem, sir.
Good. We can use parallel access theorem. But to apply parallel access theorem, you need two parallel axes, one of which is passing through the center of mass. So let's visualize that axis. Do we know the moment of inertia of a disk about this axis? We know. If its mass is m, radius is r, it is mr square by 2. Okay. So now all we need to do is first find out the mass of this small disk. Radius you already told it is r by 2. That's good. We need the mass. Once you know mass and radius, we can express, you can express ICM. The formula is mass into square of radius divided by 2. Find out its mass first. Then you will know ICM. Once you know ICM, you will be able to tell the value of I, because I is ICM plus MD square, where D is this distance, which is nothing but R by 2, radius of the small disk. Okay. Vanilla and Aishwarya don't answer. Anyone else? How can we express the mass of this small disk? Small disk is a part of the bigger disk. How to express the mass of this small disk? See, we had done this in center of mass also. How do we express the mass of part of a system? Like, how did we used to write, express the mass of dm while deriving center of mass or moment of inertia? Okay. Vanilla,
So
if
we
you're
convert it in
yeah,
terms of dy.
convert in terms of
dy.
there in that integral we had to convert in terms of dy. Okay. And to express dm in terms of dy or dr or dA, what do we first look at? We first look at what kind of mass distribution it is. Rishi, tell me, what kind of a mass distribution is a disk?
Uh, Linear, sir.
What are you saying? Hey, how can you bend a wire and make a disk? How will it be a linear mass distribution?
No, it's volumetric.
There are three options: linear, aerial, volumetric. You told the two wrong options. It's an aerial mass distribution. Mass is spread over a surface, no? The disk won't have any thickness. Thickness is negligible. It's an aerial distribution. Okay, fine. And in aerial distribution, what we do is small mass by small area is equal to total mass by total area. Fine. So mass of the small part divided by the small part's radius is r by 2. Therefore, its area will be pi into r by 2 squared, which is pi r square by 4, will be equal to total mass divided by total area. Okay, or you can simply say this way. Since the small disk's radius is r by 2, half the big disk or half of the full disk, its area will be 1/4 of the full disk. So if the full disk mass is m, then the small part's mass will be 1/4 of it. Because area is 1/4, mass also will be 1/4. Okay, so small m is capital M divided by 4. Right. Next is ICM, moment of inertia about the axis passing through center of mass. Now the formula for a disk about that axis, uniform disk about that axis, is mass into square of radius divided by 2. But here, what is the mass of this small part? M by 4. What is the radius of the small part? R by 2. Square it divided by 2. So that becomes m by 4 into r square by 4 whole divided by 2 becomes mr square by 4 is 16 by 2 is 32. That's the moment of inertia about that axis. But it's not that green axis that we are calculating about. We want about the orange axis. We'll have to use the parallel axis theorem. Therefore, that orange axis moment of inertia will now be ICM is mr square by 32 plus, okay. How much will md square be? Vanilla, you tell. What should we take in place of md square?
mr square by 16.
Good, very good, very good. So this is another what do you call place where students make mistakes very frequently. Since the formula says md square, what students write is m into distance squared. That is wrong. M is the mass of the system. Now this system is a small disk. Small disk's mass is not m, it is m by 4. So m by 4 into r by 2 whole square, mr square by 16, correct. Okay, so mr square by 32 plus mr square by 16 becomes 3 into mr square by 32. So what have we calculated? We have calculated the small disk's moment of inertia about the given axis. This one. Okay, now what is left is subtraction. Full disk moment of inertia about that axis minus small disk moment of inertia about that axis. Simple. Therefore, I of the remaining system, full disk moment of inertia about that axis is mr square by 2 minus small disk moment of inertia about that axis is 3 mr square by 32. 1 by 2 can be written as 16 by 32. 16 minus 3 becomes 13 mr square by 32. Vanilla, how did you get 15?
Forgot to add md square.
Oh, you didn't take that md square altogether. Fine, fine. Okay, so you are given a particular axis, then the moment of inertia of everything, whether you are adding or subtracting, should be calculated about that axis only. Okay. Is this clear to all of you? Any doubts in this problem? Rishi, did you understand?
Yes, sir.
Okay. Fine. Did you all write the results that we derived for a square plate yesterday? For square about many different axes, we had derived the moments of inertia.
Yes, sir. I wrote it.
You wrote. What about the others? Okay, fine. Let it be. Let's discuss one more idea about moment of inertia. Okay. Now, so far we had discussed three ideas. One idea is that you can slide the mass of a system parallel to any axis. Its moment of inertia won't change. Using that idea, we derived the moment of inertia of that inclined rod, hollow cylinder about its own axis, solid cylinder about its own axis, square about one side. In all those cases, we use that sliding idea. The other two ideas are perpendicular axis theorem and parallel axis theorem. Okay. Now there's one more logic that you can use. Suppose there is an axis like this, any random axis for a system. Let's consider a simple system with three particles. Okay, M1, M2, and M3 at distances R1, R2, and R3. Okay. Its moment of inertia is M1 R1 square plus M2 R2 square plus M3 R3 square. Suppose the masses of all particles are doubled. What will happen to the moment of inertia about the same axis? Vanilla, don't answer. If masses of all particles are doubled, what happens to the moment of inertia?
It gets doubled, sir.
It gets doubled, correct? You get a factor 2 here. Instead of M1, you will get 2M1. Instead of M3, you will get 2M3. Instead of M2 also, you will get 2M2. 2, 2, 2, you can take it common. So the new moment of inertia will be 2 times the earlier moment of inertia. Yusuf, did you understand this? Pawan, is this clear?
Yes, sir.
Okay. So let us generalize this. If mass of every particle is multiplied by a factor n, okay? If mass of every particle is multiplied by a factor of n, then the new moment of inertia will be n times the earlier moment of inertia. Okay. Next, what if the distances of these particles from the axis are doubled? What happens to moment of inertia? If all distances are doubled, what happens to the moment of inertia?
Sir, it increases by 4 times.
It gets multiplied by 4. See, you should not say increases by 4 times. Okay, let us discuss this point in detail. Increases, okay, I'm telling this to all of you. Increases by 4 times and increases to 4 times. There is a lot of difference between these two statements. Suppose there is some quantity whose magnitude is x. What is 4 times of it? 4x. Now, if you say increases by 4 times, it means it is becoming x plus 4x, means final value is 5x. If you say it is increasing 2 4 times, means the final value itself is 4x. That is the difference. Okay. So Aishwarya, do you want to change your answer, or you still say it is increases by 4 times?
Sir, it increases 4 times, sir.
2 4 times. Correct. Fine. So how does that happen? See, R1, if it is doubled, it becomes 2R1 whole square, which is effectively 4R1 square. R3, if it is doubled, it becomes 2R3 whole square, which is 4R3 square. Like that, the square of every distance gets multiplied with 4. Because every distance is getting multiplied with 2, their squares will get multiplied with 4. Then the moment of inertia will become 4 times or 2 square times. Therefore, if we generalize it, if all distances are multiplied by m, then the moment of inertia gets multiplied by m square. Okay. So if mass is multiplied by a factor n, the moment of inertia gets multiplied by n. But if distances are multiplied by a factor m, the moment of inertia gets multiplied by m square. Okay. What if both are done? Masses are being multiplied by a factor n, distances are also multiplied by a factor m. Then how much will the moment of inertia be? All masses are multiplied by n and all distances are multiplied by m. Then what will the new moment of inertia be in terms of the earlier one?
Nm squares.
N m square. Due to masses being multiplied by n, it becomes n times. Due to distances being multiplied by m, it becomes m square times. So it effectively becomes nm square times of I. Okay. Is this clear to all of you? Pawan, did you understand?
Yes.
Okay. Aishwarya, is it clear?
Yes, sir.
Fine. Let's make use of this. Okay, note this down first. If all masses are multiplied by a certain number and all distances are multiplied by a certain number, then what happens to moment of inertia? Okay. Now think carefully. This is an interesting question. Suppose there is a triangular plate like this. Now it could have any mass. Let's say its length is, or it's an equilateral triangle. I should mention that. Equilateral triangle of side A. Okay. So for this triangle, about this axis, let's say the moment of inertia is given I. Okay, hope this is clear to all of you. Now this triangle is made of some material. Maybe a cardboard was cut into this shape. The same cardboard, from the same cardboard, suppose you make a triangle like this. Okay, this is also a triangular plate itself. A cardboard sheet is cut. Okay. And if you are given an axis, if you're given a similar axis like this, how much will the moment of inertia of this one be? The smaller one's moment of inertia I is given to you. How much will the moment of inertia of the bigger one be? This is also an equilateral triangle, but its side is double the side of the other one. And I'm telling you, it is cut out from the same cardboard. Okay, keep that point in mind and think of an answer. I'll give you all 2 minutes. Type your answers in chat. Okay, I'll give you all a hint. You have to use the idea that we just discussed. Okay. If the mass of every particle is multiplied by a certain factor, moment of inertia gets multiplied by the same factor. If the distance of every particle is multiplied by a certain factor, moment of inertia gets multiplied by the square of that factor. And if both happen, it becomes nm square. Okay. So that idea has to be used in this problem. Okay, let's discuss. Pawan, tell me, what is the difference between the two triangles? Or what are the differences between the two triangles?
The side length.
Okay, length is doubled. So you can say that we are doubling the distance of every particle from the given axis. Yes or no? You take this particle, for instance, it was at a distance of a by 2 from the axis initially. Now that particle goes here. The distance becomes, the side is 2a now. So this distance becomes a. So it's like distance of every particle is getting doubled from the axis. Okay, that's one difference. All distances are doubled. Any other difference between the two triangles? I'm telling you, they are cut out from the same cardboard.
So the masses are also
Masses will be different. One is a small triangle, one is a big triangle. Masses will be different. Okay, it's not like the smaller triangle is being stretched to make a bigger triangle. These are two separate triangles. Okay, cut out from the same piece of cardboard. Okay, and fine. Let's say the original or the smaller triangle has a mass m. Can any of you tell me what will be the mass of this bigger triangle? All of you, I want answer from all of you. Type your answer in chat within 1 minute. If small triangle's mass is m, what do you think is the mass of the bigger triangle? I want answers from all of you. Think carefully and give some answer by 1 minute. Okay, Vanilla, you have given the answer correct. Then correct your answer for moment of inertia. The answer you gave earlier is wrong. Others, what do you think will be the mass of the bigger triangle? I got only 3 answers. I have to get 2 more answers. Quick. Pawan, Yusuf, send your answers quickly. Okay, fine. Rishi, can you explain your answer? You said its mass will be 2m. Why?
So because
Hmm.
the side is also doubled, but
Is this a linear mass distribution? That mass becomes proportional to distance. What kind of mass
no,
distribution is
sir.
a triangular plate?
Aerial.
Then you have to think in terms of area, no? What is the ratio of areas of the triangles? If side is doubled, what happens to area? Area of an equilateral triangle, how much is it? Root 3 by 4a square. Is that correct? Half base into height, half into base is a, Height is a root 3 by 2. Okay, root 3 by 4 a square is the area of an equilateral triangle. Now, if side is doubled, it becomes 2a whole square, which is 4 times. So their areas are in the ratio 1:4. Masses also will be in the ratio 1:4. The mass is 4m. Okay. So now see what happened. The mass gets multiplied with 4 and the distances get multiplied with 2. Okay. Now if mass gets multiplied with n and distances get multiplied with m, then the moment of inertia gets multiplied with nm square. Okay. That's all. Therefore, the moment of inertia of this new triangle about the given axis is n. N is the factor by which mass is multiplied. M is the factor by which distances are multiplied into I. So the answer is 16I for that triangle. Okay. Next. Another problem related to this one. Again, consider this same equilateral triangle of side A. Its moment of inertia is I. This problem is also based on this idea itself, but there is some extra, there are some extra tricks that you need to apply. Let's see if any of you can do it. That is given to you. Moment of inertia I is given to you. Okay. You have to find out the moment of inertia of this hexagon now. And how are they related? I'm telling you that the hexagon's side is also A itself. Okay. And about which axis do you have to find out? So wait, let me mention here. It's a hexagon of side A. And you need to derive its moment of inertia about an axis which cuts it into two halves vertically. Okay. Think carefully and answer. If you can answer this question correctly, you don't have to pay fees for the next month. Try. I'll give you all 4 minutes to solve. Okay, some of you gave some answers. Let's discuss the ideas that you used. I see most of you found out the mass of the hexagon. Okay. Okay, tell me, Rishi, what was your idea?
So ratio of hexagon is no ratio of triangle is to ratio of
Triangle hexagon ratio directly you can't take. If the same shape is enlarged by a certain factor, then you can use. Triangle hexagon are different shapes. No, you can't use that idea directly. Okay, Vanilla, what was your idea?
Sir, I thought the hexagon was made up of 6 equilateral triangles and
That is correct. Hexagon is a combination of 6 equilateral triangles. And then
out of the 6 equilateral triangles, 2 equilateral triangles, moment of inertia will be I only, sir.
okay, out of these 6 equilateral triangles, okay, let's visualize the equilateral triangles first. And hexagon is a combination of equilateral triangles, 6 equilateral triangles. Just a moment. Yeah, fine. Now, you have to find out moment of inertia of the hexagon about the given axis. Basically, it's the sum of moments of inertia of these triangles about the given axis. Now you look at these two triangles. This one is the exact same triangle that is given to you. Okay. So this one's moment of inertia is already I. And for this one also, it will be I itself. It's the same axis. It's a triangle is inverted. That's fine. But it's the same axis, no? Dividing it into two symmetric halves. So this and this are I and I. So they will contribute to I. Those two triangles will contribute to I. Okay, till there your ideas are correct only. After that,
Sir, I used parallel.
okay, you tried to use
Parallel axis
parallel axis.
theorem.
You tried to use parallel axis theorem for the remaining triangles. That idea is good only, but you can't implement it. Implementation will be difficult because First, for parallel access theorem, you need for parallel access theorem is ICM plus MD square. No, ICM is I only. Distance also you know, it is half of the side of the triangle. But what is the mass of this triangle? That is not given to you. And you need not know the mass also. Without knowing also you can answer. Okay, any other ideas, anyone? Okay, fine. This requires a little bit of thinking outside the box. Let me explain how. Consider this hexagon. You know there are 6 triangles in this hexagon. Okay. And those triangles, their sides are A only. Each equilateral triangle is of side A. But if you add 2 more triangles, you get something interesting. Just a moment, let me adjust this. Add 1 triangle here and 1 triangle on the bottom side. So totally 8 triangles will be there. 6 already there in the hexagon, 2 more. But still, that won't. Okay, wait, why am I not able to rotate this? Just a second. But let's see how this is actually helpful in solving the problem. Okay, so it's a combination of 8 triangles like this. Now for the small triangle, we know the moment of inertia about the given axis is I. Now, okay, any idea, anyone? Now, what to do next? Okay, fine, not an issue. What we are now going to do is treat it as a combination of just 2 big triangles. One is this. The other is on the bottom side. And what is the axis about which we want the moment of inertia? This vertical axis, the y-axis. That's all. And how much ever moment of inertia that upper part has, the same moment of inertia the lower part also will be having. Okay. And that upper part is an equilateral triangle of what side? 2A. And we know its moment of inertia. This one, 16I. If for that one triangle, small triangle, it is I, then for this big triangle of side 2A, it is 16I. Therefore, this upper part's moment of inertia is 16I. The lower part's moment of inertia also will be 16I. So for this diagram, the total moment of inertia is 32I. Okay, but this is not the system whose moment of inertia you were asked. You have to remove those 2 triangles. The upper one, okay, this has to be removed and this has to be removed. If you are removing them, you are removing I and I. That's all. The answer is 30I for that hexagon. Is the solution clear? To the given hexagon, we added 2 triangles first in order to make it a collection of 2 big triangles. Why? Because for each big triangle, we already knew the moment of inertia. Okay, 16I, 16I. Therefore, for this collection of 8 triangles, it is 32I. Now from those 8 triangles, we have to remove the upper one and the bottom one, topmost and the bottommost. Remove them, you will be removing I and I. So the answer will be 32 minus 2, 30I. Okay. Next. Suppose there is a rectangular plate. Okay, you just think about this solution. I'll just get the diagram for the next one. Okay. Suppose there's a rectangular plate like this. Again, 2-dimensional system. I'll have to give you its mass and dimensions, right? So assume the mass is m, total mass is m. One side is A, the other side is B. Okay, and what do I want? I mean, about which axis should you calculate? Diagonal. Derive its moment of inertia about the diagonal. Try this. This is also an interesting question. Again, for this also, if you can answer within 5 minutes, okay, I will give you some gift. We will see. Think carefully and solve, all of you. This involves some ideas that we discussed about moment of inertia so far, and also a little bit of geometry. Okay. Any ideas, anyone? If you have started working on it, how are you trying to solve? Okay, for how many of you moment of inertia has already been taught in your schools or coachings? I won't trouble you much. I just want to know, that's all. None of you learned about moment of inertia before this. Okay, fine. Fine. Why I asked is, like, mostly if you are part of any coaching system, then they would have taught you the moment of inertia of a triangle about one side. You can think of the rectangle as two triangles and answer. Okay. But anyway, we have not discussed moment of inertia of a triangular plate yet. Okay. Ratio based problems we solved, but exact value we still don't know. And we don't need also. There's an interesting way to solve this. Listen carefully, all of you. You need the moment of inertia of a rectangle about its diagonal. Let the answer be I. That is what we are looking to derive. Okay. Now this rectangle or a rectangular plate can be considered as a combination of 4 smaller rectangles like this. Rishi, what do you say? Yes or no? Can we consider the given rectangle as a combination of 4 smaller rectangles like this or not?
Yes, sir.
Can be done. Okay. See, the diagonal was drawn with freehand, so it may not be accurate. But you can think of it as a combination of 4 smaller rectangles like this. Okay. Hope you all are okay with this. Next. Okay, let me adjust this. Okay, you all think about this. If the full rectangle's diagonal moment of inertia is I, then for each of these small rectangles, what will be the moment of inertia about their diagonals? Full rectangle diagonal moment of inertia is I. Then for each small one, how much will it be? Now that is a ratio based question.
I by 4.
No. I by 4, like on what basis did you say I by 4? Because the dimensions are half.
Yes.
But mass also will be 1/4, no? Small piece will have small mass. Okay. So yeah, dimension wise, the full rectangle and these small 4 small rectangles that we considered If the full rectangle's length is A, then the small rectangle's length will be A by 2, width will be B by 2. Okay, so dimensions are getting halved. Due to that, moment of inertia becomes 1/4. Yes, but if the full rectangle's mass is m, then the small part's mass will only be m by 4. And if mass is divided by 4, moment of inertia also gets divided by 4. So due to dimensions, it is getting divided by 2 square, that is 4. And due to mass, it is getting divided by another 4. So totally it gets divided by 16. So what we can now say is the moment of inertia of each small rectangle about its diagonal is I by 16. If the full rectangle's moment of inertia is I, this will be I by 16. Okay. Then there are two smaller rectangles which have the same diagonal as the original rectangle, these ones. So I by 16 about this axis, I by 16 about this axis, and two rectangles whose diagonals are on the sides. Let it be. Total moment of inertia is I. Now, the original diagonal is also the diagonal for these two rectangles. So this I by 16 and I by 16 will be there in that I. Plus I by 16 plus the other two rectangles that are there. Their moments of inertia about this diagonal we have to derive. Okay, let me keep this as it is. I'll copy paste. Okay. Now, these two rectangles that are left, we have to express their moments of inertia also about the original diagonal. Then we can get the total system's moment of inertia. Now, this rectangular piece, its mass is m by 4. Its side here is a by 2. This side is b by 2. We want its moment of inertia about the big diagonal. Its diagonal, okay, like this one, and the original rectangle's diagonal, they are parallel axis. So we'll use parallel axis theorem. So let's just take one of these rectangular pieces just to avoid confusion. We want the moment of inertia of this rectangular piece about this big axis. About the small axis, we assumed it is I by 6. We don't know how much is I, but we assumed it is I by 16, not 6, 16. Now, if you want to apply parallel axis theorem, tell me that small diagonal, will it be passing through the center of that rectangular piece or not? It will definitely be passing. So that is ICM for it. Okay, for that rectangular piece, that is moment of inertia about an axis passing through center of mass. What we want is moment of inertia about this axis. For that, we will have to find out this distance. That is the geometry part that I was talking about. Anyway, see, these are very difficult ideas. You cannot, I mean, it's perfectly fine if you are not able to think of all these ideas. Okay, most students cannot. Okay. In fact, no student can. If you are not exposed to such questions, where will you get such ideas from out of nowhere? Anyway, now the geometry part. We have to derive this distance in a rectangle. Can any of you help me do that? Suppose the length and breadth are known. A and B are known. How much will that distance be? This itself becomes a separate question now. You can think of it as a right angle triangle actually. It's a right angle triangle, you know, like this part is a right angle triangle. Two sides you know, and you want to find out the altitude from the third side. Okay, so let me draw that right angle triangle separately. Okay. Consider some right angle triangle like this. This side is A, this side is B, and we need this height. Any ideas? Yusuf, you don't even have to bother about all this. For NEET, this is too much. The others who are preparing for JEE, you will have to deal with such things. Yusuf, actually, if you want to leave, you can leave. Otherwise, if you think this is an interesting discussion, you can continue. The ones who are studying mathematics, any idea to derive this height in a right angle triangle? Okay. Exact angles we don't know. Had you known the angles, you could have used trigonometry and gotten that height. What I mean to say is, if you know this angle is alpha, then for alpha, this is adjacent side and this is hypotenuse. Using cos alpha, you could have gotten that height. But we don't know that angle also. Anyone? Okay, I'll give you all a minute. Think about it. Any ideas, anyone? Okay, fine. Tell me the formula for area of a triangle.
Half into base into height.
Half into base into height, correct. We don't know this height. That's okay. How much is this base?
Root
Come.
over a square plus b square.
Root of a square plus b square. So the area can be written as half root a square plus b square h. Okay. Rotate the triangle. If you rotate the triangle, you can consider this as a base. And because this is a 90 degree, this is a right angle triangle, I told you, no? If you take that as base, A as base, then B becomes the height. That way, if you see, what is the area of this triangle? Half AB. And these two should be same because it's the same triangle. That's all. From there, you can get h. Okay. So half h root a square plus b square is equal to half AB. Cancel half. H is AB by root of a square plus b square. So now we have a way to derive that height if you know the sides of the triangle. Okay, fine. Is this clear to all of you? We are just writing the area of the triangle in two different ways. It doesn't matter which side you take as base. You just have to take height from that side. You'll always get the same area. Okay. Fine. So if the sides are A and B, this is the height of the triangle. Okay. A and B were sides of the original rectangle. But for this small rectangular piece, the sides are A by 2 and B by 2. So in that case, what will the height be? Let's call it as h dash. It will be, or let's call it distance d. We are going to use that in the parallel axis theorem. Let's call it the distance d will be a by 2 into b by 2 divided by square root of a by 2 whole square plus b by 2 whole square. Okay, a by 2 into b by 2 is ab by 4 divided by square. Okay, why are we struggling so much, wasting time? Will it not be half of the big rectangle's height? It will be. Big rectangle height is ab by root of a square plus b square. If all dimensions are halved, then this height also will get halved, no? We can use that. Okay. This distance d is therefore half of ab by root a square plus b square. We got the distance that we need. Why did we need the distance? To express this rectangular piece's moment of inertia about the original diagonal, the big diagonal that I have drawn. So, okay, let me copy this. This rectangular piece that is there, which is not lying on the original diagonal, it's lying on the side. Okay. Its moment of inertia about this axis will be, its moment of inertia about center of mass is I by 16 plus its mass is m by 4 and the distance is half ab by root of a square plus b square. We have to square the distance. So it becomes half squared becomes 1/4 and a square b square by a square plus b square. That is its moment of inertia about the original diagonal. And how many this kind of rectangular pieces were there? 2. One is this and one is this. They will both contribute the same moment of inertia about the original diagonal. Okay. So these two pieces, the ones I am shading in green, they were contributing I by 16, I by 16 to the original rectangle. And the other two pieces are contributing this much each. And we assumed, like, what was I? I was the original rectangle's moment of inertia, okay, which we are trying to express as the sum of these four moments of inertia. Okay. Therefore, I is equal to the two rectangles which were on the diagonal, they contributed I by 16, I by 16. So I by 16 into 2 plus the two rectangles which were not on the diagonal, they will contribute 2 times of this entire expression. I by 16 plus m by 4 into 1 by 4 is m by 16 into a square b square by a square plus b square. That's all. Now you just have to solve this equation for I. You get I is equal to right hand side. I by 16 into 2 is I by 8 plus, again, multiply that second bracket with 2. You get another I by 8 plus 2 times m by 16 is m by 8 a square b square by a square plus b square. Now I by 8 is I by 4. Send it to the other side. You get 3I by 4 is equal to m by 8 into a square b square by a square plus b square. And 4, 8 cancel 2 times. Send the 3 this side. Therefore, I is equal to m by 6 a square b square by a square plus b square. This is the moment of inertia of the rectangular plate about its diagonal. Okay, we see again, this is a completely different idea that we used. I assumed the required moment of inertia is I. Then I split the given rectangle into 4 smaller rectangles. For the original rectangle, if it is I, then for each small rectangle about its own diagonal, it is I by 16, I by 16, I by 16, I by 16. Now, 2 of those smaller rectangles were contributing directly. The other 2 were contributing indirectly. So we had to apply parallel access theorem for the other 2. And that's how we did all that. And we included mass, distances and all. We got the answer as this. Okay. But observe, there's something important here. What is this? A square b square by a square plus b square is nothing but h square. Therefore, the answer becomes total mass into h square by 6. That's all. Where h is that this height. Okay, I'll send you the notes for this. Do this derivation once on your own. Okay. See, it's highly unlikely that they will ask you questions like this in the exam, but in final exam, like maybe JEE advanced, they can ask. In normal exams, they won't ask. And I told you, moment of inertia is one such quantity on which they will ask you separate questions, not even linked questions. But now you can understand why. There are so many different techniques that can be used to derive this quantity called moment of inertia. So why can't they test any one of those techniques? Okay, they can. So be very thorough with moment of inertia. Tomorrow or next class, we will discuss some applications of this. See, where did we first come across moment of inertia? We came across moment of inertia when we discussed kinetic energy in rotation. The formula was half I omega square, where I is the moment of inertia of the system. And from there onwards, we discussed moment of inertia of different systems about different axes. So if you know moment of inertia, you will be able to write rotational kinetic energy. And if you can write kinetic energy, you can apply work energy theorem, you can apply mechanical energy conservation and all. Okay. So next class, we will discuss problems based on mechanical energy conservation and work energy theorem in case of rotation. Okay.